Is everyone awake? On the count of 3, let's say flight software. 1, 2, 3. Flight software. Now I know you're all awake. So we're here to talk about flight software. My name is Thea-Martine Gauthier. I'm the HPSC software architect. I work on a very small team of people in conjunction with a very large team of people at Microchip Technology. And we have developed this processor called HPSC, High Performance Spaceflight Computing. This is a project funded by NASA through STMD's game-changing development. And I'm going to talk a little bit about the flight software and software aspects of it. I see some of my compatriots in the audience. Some people from Microchip are here, which is lovely. Is it going to work? Does it work? It doesn't work. Oh, well. So here's the agenda. I have a lot of slides to get through, so I'm going to talk really fast. In general, I talk pretty fast anyway, but I'm going to try and talk pretty fast. I hope that's okay for all of you. So what is HPSC? HPSC was engineered for the AI edge. If we're talking about high-performance computing, any kind of processor that you put in space that's designed to do autonomy or AI has to have significant high-performance computing capability. And we think we've put this into HPSC. HPSC rivals a lot of GPUs, commercial or currently available GPUs, and also desktop processors. We are measuring HPSC all the time. We do a lot of different things to measure HPSC. Well, we did a lot of different things to measure HPSC while we were developing it. HPSC has incredible performance, 64 gigaflops of double precision, 128 single precision, and 256 half precision gigaflops. It's designed for AI workloads. It's also designed for doing high-performance computing in space. You can make a high-performance computer and put it in a hab or on a gateway with HPSC, and you can use different kinds of commercially available or open source software to meld all that together and make it look like one big computer. HPSC has significant fault-tolerant and flight software features, and that is one of the reasons why I'm here to talk about it. I don't imagine that any of you are HPC people. Who's an HPC person? One person, that's it? So you're all just flight software people. So do you dream about command and data handling? Okay. I don't know. So my background is in high-performance computing. I'm basically an applied performance engineer. I used to work in the applied performance group at Intel a long time ago. I don't really do that. I don't work on Intel stuff anymore. I mainly work on RISC-V and ARM architectures now. HPSC is very good at doing lots of different things. And one of the reasons for that is you can scale HPSC up and down. It's got a lot of ways to turn it into something that you would like to have it. You can switch a lot of HPSC on and off for various reasons. It can be in a rover, a heli, a lander. You can make high bandwidth instruments from it. You can put it in small sats, and it has a way to tweak its power to do almost anything you want. You're all taking pictures, but these slides are available. That's okay. I'm here to tell you that HPSC sets the bar for advanced autonomy at the edge. There's no other currently available nor future planned spaceflight processor that has the features that HPSC has, and I hope to convince you during this presentation. There are 6 big things that HPSC, the 6? Yeah, 3 and 3 is 6, right? 6 big things that HPSC offers. It's designed for high-performance autonomous spacecraft, and there's a lot of features for that. It's got advanced autonomy through its AI capability. It has serious fault tolerance and also it's one of the first microprocessors, commercial microprocessors in existence that has ARINC 653 built inside the processor. Significant time and space partitioning as well. Well, I said time, but it's a rad hard by design using multiple hardening techniques. And between NASA and Microchip, we're developing a huge ecosystem of partners to bring this capability to all future spaceflight. Also, the software stack, which is where I come in, is one of the most advanced and modern software stacks. I don't know about y'all, but I hate embedded development. Who hates embedded development? Yeah. Who has nightmares about cross-compilation? Thank you. I feel like my life is an endless succession of resolving dependencies on the target. Okay. Enough about that. What's so cool about HPSC, you asked me? HPSC has a lot of key features. First of all, it's a 10-core processor. There's 8 main application cores. There's something called the system controller, which is designed to monitor the health and safety of the processor. It's on all the time. And then there's a security processor, which takes care of security stuff. We're not really doing a lot of security right now at NASA or JPL, but we can see that coming up. And so HPSC has very interesting and lovely security features. A lot of this has, we took a lot of advice from the DoD and also from Microchip's partners to understand what needed to go in there, and we think we put that in there. The other cool thing about HPSC that maybe you didn't know is that there is a complete TSN 240 gigabit enterprise-grade TSN switch. It's actually from automotive, the automotive line of Microchip products. It's an ASIL qualified chip with RDMA support, and I'll talk about RDMA support in a second. Loss of fault tolerance, radiation tolerance, dynamic power profiles, and precise power control. You can turn on and off almost anything in the chip that you like, when you like, to do what you like, which is important. And I already mentioned defense-grade security. Lots of stuff over here. I'm not really going to talk about it. You can sort of look at it. So here's what I call the fault-tolerant pyramid. Starting at the bottom with process and technology, and also moving up through different things, we have a lot of fault-tolerant features inside HPSC. Most of them are built into the device, for instance, like the kind of flops that we're using to create the device, or the node that it's being made on. Hardware scrubbers are working in the background. Some of it is more explicitly under software control, and a lot of it is for high availability, for failover, for monitoring the device, and for doing really other interesting things like NMR applications, which HPSC can do. We have dynamic power control. So there are 70 active gated regions on this chip. If you don't want the Ethernet switch on, shut it off. If you don't want endpoints on, shut them off. If you want to turn PHYs off, shut them off. If you are not interested in using the chip in a certain way, you can turn it up and down depending on how you want to use it. So there's a very small standby sleep mode. It will just sip power, or you can run flat out and get the highest performance that you want. And that's the sort of top line numbers that I talked about before. So you can tweak these by mission phases, and I'm going to talk about that in a second. One of the key defining features of a high-performance computer is how fast you can ingest data and how fast you can get results, which I call time to value. So HPSC, due to its switch and due to its RDMA capability, can sync 80 gigabits per second into the switch without CPU intervention using the devices that we have on here. And so what this means is that if you want to make a high throughput sensor, or you want to make some kind of large SAR array, or you want to do some kind of science where you have high bandwidth sensors, which is really what HPSC was designed for, you can ingest that data very quickly, and the CPU does not have to be involved with that. So you'll see a lot of spacecraft processors, and they have a 1 gig Ethernet, or they have two 1 gig Ethernets. We have 16 ports of 10 gig TSN Ethernet on this switch, and another 4 endpoints for that. So it's a huge amount of data that you can ingest with this. All for TSN, time-sensitive networking. Who's familiar with TSN? Some people. TSN is just a way to control the timing of things on the Ethernet network. Guarantees delivery of time, guarantees delivery of packets, so it's very sensitive to the needs of a spacecraft. One of the coolest things about HPSC is, due to its architecture, you can split HPSC up into many different ways. You can split it directly in half. You can have DCLS pairs, which are dual core lockstep, which is where one core shadows another core, and if there's any execution mismatch between the two cores, it will squelch the output of the core so that bad data does not get into the rest of the system. There's lots of different ways to set up HPSC, and most of the OSs support all of these different ways. In reality, though, I think we'll probably use between 1 and 4 of these, although all of them are possible. The nice thing about some of these is they allow for high availability or failover configurations. They allow for things like mixed criticality. So if I want to split HPSC in half and run 4 cores of Linux on one side, flat out doing AI/ML work, but on the other side, I need to land the spacecraft with some kind of real-time OS, I can do that. And the two won't intermingle because I've split the architecture down the middle. The other interesting thing about HPSC is you can have many, many different configurations of HPSC on tap. And so each one of these configurations is a confluence of all of the different operating systems, all of the data, all of the pieces that would get loaded into the cores and execute. And then under flight software control, you can ask HPSC to boot to the next mission phase or to do something different. So for example, I'm cruising on the way to where I'm going. That's one software load. And then I want to land. That's another software load, which much higher criticality. And now I'm on the ground. I want to move into a system check mode where I'm going to check out everything. That's another thing you can do. So you can move between these and you can get precisely what you want with the kind of power control that you want for whatever mission phase you're about to execute. Okay, so we're here to talk about software, right? So HPSC embraces modern high-performance standards, which means we have modern compiler, LLVM. We have the latest versions of LLVM, the latest versions of Linux. In fact, if you're using Linux and you're comfortable with that, you can fly any language you want. I think Kelly was talking about her engineers asking her if they could fly different languages. You can do that if you want. HPSC has broad system support and a hypervisor also. We have Zen hypervisor on board. So here's a nice logo array for you. I didn't show one yet, but this is my logo array. Most of HPS software is completely open source. There are parts that are not open source, but they're not, that important for software development in terms of the day-to-day of what you have to do. So, for example, all of the changes for HPSC and the SoC for Linux will be upstream to Linux. Same with RTEMS. VxWorks is, of course, a commercial OS, but that will be handled separately. And we also have bare metal available. So speaking of these things, this is the scope of support for HPSC. We have a complete Debian distribution. So if you get an HPSC evaluation board and you boot it up, you're booted into Debian. Instead of resolving dependencies by cross-compiling, you can just apt-get install whatever dependencies you want. And then when you think you've got your software load, you can make your own custom OS with Yocto overlays that we provide. So you can go from a full-fledged dev environment for Linux down to a very cut-down one with Yocto. And the Linux that we're using since, I think, was 6.13, Ken, correct me if I'm wrong, we got the RT patch, which is mainlined up in Linux. So the default Linux OS will be RT. VxWorks, of course, VxWorks 7, RTEMS, and Zen. So you can run most of these OSs on top of Zen as well, or you can just use the ARINC 653 Zen support. And we also have the Sci-Fi bare metal SDK available if you want to run bare metal, or if you've got very, very, very tight control loops, 1,000 hertz, whatever control loops, you can do it that way. Language support, all the usual suspects. C and C++, which we'll never escape from now until the end of time. One of the coolest things of HPSC is that it's completely programmable in OpenCL. So you can target the on-chip cores and any accelerators or GPUs that are attached to HPSC using OpenCL, which means that this allows you to test stuff on your desktop. And if you're writing in an OpenCL, it will take advantage of whatever resources are available on your desktop machine. And then when you move it over to HPSC, it will use the resources available on HPSC. And if you're very clever in the way you do this, you're doing dynamic configuration of how many cores, threads, things like that you have, so it should be able to adapt. I have to mention Python. At the beginning of HPSC, almost 3 years ago, when I asked people inside NASA JPL what they wanted to see inside HPSC, one of the most interesting responses, we just want a laptop in space that runs Python. Okay, we got that for you. HPSC software stack, pretty extensive. This is what I would call the HPC dev software stack. I'm not really going to go through this, but just so you know, we've thought a lot about this. I sort of took all my experience and then went out and we did a ton of use case, ton of research about what needed to be in here. We also wanted it to be modern, programmable, easily accessible, not obscure, not opaque, so that you could work on this stuff in a reasonable way without wasting a lot of your time. So we think we've come up with this. And so that's this is sort of the culmination of all of those things. I would like to call your attention to the high performance libraries like OpenBlast and Eigen and TF-Lite and XNNPack. Those are optimized for the cores that are on this machine. So I don't know how many of you are looking at flight software where you've written your 100th iteration of a matrix multiply, but no longer is that the case. You can just call OpenBlast and it's optimized to the width of the machine. You can get the fastest performance for that matrix multiply. So whatever you're doing, don't implement it yourself. Call these libraries that we have, and then you'll be assured of all the performance for HPSC. HPSC, the analysis by mission phase is pretty important. So I mentioned CDH, yes. GNC too, yes. Latency critical, minimum jitter. HPSC has a lot of features for that. EDL, HPSC has a lot of features for that. Science data processing, a lot of features for that. I won't read them, but what I will say about HPSC is that it has unparalleled spacecraft command and control features. The onboard timer system, the time and space partitioning, all the fault tolerance features, it doesn't exist anywhere else. In fact, I will go so far as to say that the onboard timer and time and space partitioning features are not available on any microprocessor anywhere. This thing is purpose-built for space missions. Planning and scheduling, of course, fault protection, AI, ML as well. You can all parse this out. One of the interesting things to note is that HPSC was designed for space VPX and the new space VPX SOSA consortium work that's coming out, sponsored in part by NASA. That's an industry consortium to get together what a hardware platform would look like so that we can just build things out of Lego blocks rather than building them all ourselves. And I'll talk about more the ecosystem at the end of this. But really the idea is that you can have lower cost, faster time to market by just getting stuff that we are pushing forward through the ecosystem. One of the things I want to call out is that HPSC kind of looks like a GPU. The interesting thing about HPSC is that it can execute scalar, vector, and AI/ML workloads all at the same time on the same cores. There's no difference between them. It's just because of the vector unit that's inside HPSC that makes this possible. So what does that mean for people who are used to using 3 tool chains to get things done with different kinds of things? Well, in HPSC, you have 1 tool chain, and especially if you use OpenCL, that's even great for off-chip GPUs. You can address that GPU with OpenCL using the same tool chain. So we are using the X280 or X288 core complex from Sci5. This particular core, like I said, is designed for AI/ML. There's a lot of fancy features for the X288, which we asked for, and they put in, for us because we paid them money. Some of the things I talked about have to do with splitting up the architecture, making it very useful, adding more fault-tolerant modes. The couple biggest things are dual-core lockstep, which I mentioned already, the cluster splitting, the hashing functions. WorldGuard is very important. I'll talk about that in a second. Software virtualization. We also have CXL, which is a way that accelerators or GPUs can share the same memory space coherently with the processor. So that's very interesting. And so it really looks like 2 clusters of 4 cores each, and then you can have 4 pairs of dual core lockstep. All of these buses down here are very wide and very fast. So for flight software types in the room, who I'm assuming is everyone, HPSC has a lot of close memories. Now, what does that mean? That means that, as you all know, the relative time of everything is super important. And accessing stuff off DRAM takes a long time, but accessing things that are right next to the core don't take so much time. So these close memories have a very small cycle load to use latency. There's something called the ITIM, which is 32K instruction cache. You can put, often used things inside this cache. And then the data and results can be stored in the DLS, which is a data local store. There's 128K for each core. And then if you put HPSC into a cache isolated mode, you can use the L3 as a scratch pad, which is kind of interesting. So If you want to do mixed criticality, if you've got very tight loops, if you want to guarantee that there's the minimum jitter, or more, you want to force more deterministic latency into the system, you can use these close memories to address some of your concerns about instruction bubbles, latencies while traversing across the NOC into DDR and other things like that. Here's the big example. I know this looks crazy, right? You're like, this is crazy. It's very colorful though. So this is an example where HPSC is split down the middle. The left-hand side is running Linux in SMP mode. And that can be, running CFE, CFS, or F prime, or whatever frameworks that you want to run. You can take advantages of all the things that I've talked about so far. And on the right-hand side, we have a split with 2 DCLS pairs running VxWorks. So right-hand side, mixed criticality. Deterministic latency is very controlled. On the left-hand side, Linux is Linux, so it's not very deterministic, but it is relatively high performance. So, you're sort of landing the spacecraft on the right-hand side, but on the left-hand side, as you look down in the camera to find out where you're landing, AIML is recognizing features and things, passing that back to the flight's software side to figure out where the best place to land is basically. So these two things working in concert is this mixed criticality example. You could also use this example as a high availability failover. So if you're running on the right-hand side, if you're running 2 of the same operating systems, one is sort of the leader and the other one's sort of the follower. If the leader dies, for example, the follower could take over under flight software control. HPSC has the best notion of time in the entire universe. No, okay. HPSC has an amazing notion of time. There's 3 onboard timers. And between these 3 onboard timers and the ability to synchronize between the timers, it is possible to keep track of very, very, very small timescale events and also coordinate command and control across cores, even in split modes. Not to mention that we have this thing called the ARINC block, which I'm going to talk about in a second. The ARINC block is tied to something called the application DMA processor. What this really means for you is that if I have an ARINC 653 schedule, major, minor, subminor frames, and I have DMA transfers that can only occur in certain windows, you can force the hardware to squelch or prevent DMA transfers from happening outside their window. So that's really important. The other thing I should say is one of the interesting pieces about HPSC, which I love, is the notion of this M-time register, which is precisely the same at any instant on the device. So if I'm running completely different operating systems on many places in the chip, and I want to grab time at the same place, even though I'm running different OSs, that notion of time will be precisely the same. Precisely the same. And so this is connected to the HP timer, which is a 64-bit monotonic timer with 20 nanosecond resolution. That thing's always counting up, never going backwards. Even if I take a core out of contention or I do a warm reset, I still get back to where I need to be with that value. This allows coordination of lots of very short time scale, or it allows coordination between different parts of the chip using different operating systems. Very important. VxWorks can also use the ARINC block to clock its execution. So here's a view of the ARINC block. There's a couple registers, as you can see here. And what this allows you to do is do, like I said, major, minor, subminor frame stuff. But at the end of a subminor frame, for example, if I want to cause an RTI, I can do that. At the end of a major frame, if I want to wiggle a GPIO, I can do that. Or if I want to attach this up to the DMA engine, I can absolutely do that too. So between this is our time partitioned piece. We also have a space partition piece, which I'm going to talk about in a second. This allows you to have very strong protection for time and space. One OS can't run over to the other OS, and since you can split HPSC in various different ways, it's very difficult to force HPSC to have contention all the way through the device, all the way out to the peripherals. One of the reasons why is because there's something called WorldGuard. WorldGuard is the way to guarantee that, so I'll take a step back for a second. An SoC is a bunch of disparate pieces connected by this thing called a NoC, a network on chip. It's like a big crossbar switch. And so the CPU is connected on there, the DDR is connected on there, the PCIe ports are connected on there, serial ports, all these things are connected. So you can say, hey, I want to make it so that for this side of HPSC, I only want to use this DDR interface, and I want the memory map to look like this. And for this side of HPSC, I want the memory map to look like this. I want to use these peripherals. And the great thing about this is, if one side tries to use the other side peripherals or memory, it's not possible. Not possible. So here you see 4 WorldGuard regions where some of these things are shared. For example, in World 2, you see World 2.3 data as a shared piece.
Yeah, I just wanted to give you a 2-minute warning.
Oh my God, I'm so far behind. Yeah, so at least you didn't come up here and like mess with the computer. That's okay. I'm happy to be out of time.
I'm trying.
So this lets you basically control access to HPSC peripherals. And this is not something that is a software thing. This is built into the hardware all the way up through the cores down to the very end. So it's impossible to violate it in any way. There's no software way to get around it. AppDMA is pretty impressive. We have 2 AppDMA engine. Each is an 8-channel direct memory access controller. The cool thing about this is you can set AppDMA off on a task to take some memory from someplace and put it someplace else. But in the meantime, while it's doing that, it's going to rotate it, flip it, transform it, do all this other stuff to you. As you all know, when you ingest sensors into the spacecraft, the way that it comes in is not the way the processor likes it. So this lets you put it in the way that the processor likes it behind the scenes without CPU control. CPU messing with it. So by the time the CPU has to mess with it, it's in exactly the way it needs to be. We also have AIML support. TensorFlow and XNMPAC. So the cool thing about HPSC is it's got these 4 instructions, which make it possible to do, for certain types of matrix multiplies, 1 teraflop of performance for 8-bit CNNs that use 8-bit resolution. That's pretty impressive, considering that this device only runs at 1 gigahertz. HPSC has an insane debug system. It's the best that I've ever seen. There's also a possibility to debug HPSC in space. If you email me or talk to me after, I can tell you more info about this. One of the great things, and thank you so much, Microchip, is HPSC project asked for these very extravagant, kind of slightly expensive evaluation boards for us to test out in the lab. But Microchip said, nah, we got to make this thing available for cheap for people. So this is a 3K eval board, which you can have on your desktop. And it gives you access to, I would say, 86.375% of all the features on HPSC. So you can put this on your desktop. You can have HPSC on your desktop and develop for it, no problems.
Yeah, so we are unfortunately out of time.
Okay.
But I do want to give you another 20 seconds if you want to say any parting words. And
yes.
All your slides are available online, and people can continue the conversation on Slack.
So what I will say is HPSC loves you, loves all of you. There's a NASA white paper if you're interested. There's also the Microchip website. And I made a soundtrack about what HPSC would sound like in space. Feel free to go listen to it. It's very moody ambient music like me. So I guess that concludes my remarks. If anyone has any interest in HPSC or you want to talk to me, you can come up after. I'm happy. I'll be here most of the 4 days, I think. Do we have time for questions, or did I burn all the time?
I think we went through all the time.
That's okay.
But there are questions on Slack, and so we can answer them on there.
Okay, perfect.
Thank you. Appreciate it.
Thank you.